really very, very happy to be here. It's my second time, I should say. And so I will give a series on introduction into syzygies. Well, I have to apologize. I see that there are many people in the room that know these things, or at least what I'm going to talk about in the first part. So I apologize from the beginning. So the subject of these lectures will be syzygies, and of course the first question is, what is a syzygy? So nowadays the best way to find out what's the meaning of a word is to Google it. And if we Google the word syzygy, we find many results. And the first result is a link to the Wikipedia page. So you click on it and you find many other results. For example, the word syzygy is used in poetry as a combination of two metrical feet into a single unit. Or in fiction, it was an episode from the X-Files. I haven't watched it, I'm afraid. In music is a Japanese band. In philosophy is a concept due to Vladimir Solovyov to denote close union. In business, it's an American IT company. In science, in biology, it's an important notion and means a pairing of chromosomes. In astronomy, and that's the origin of the that comes from ancient Greek. In astronomy, it means a straight line configuration of three celestial bodies. So that's somehow the meaning of this word, a straight line configuration. And finally, we get to the math notion, to the math word, which is the relation between the generators of a module. So the mathematical term is actually due to Sylvester, so that's the first encounter of this notion of syzygy, and I'll just quote from Sylvester. This means, so he says that the members of any group of functions more than 2 in number whose nullity is implied in the relation of double contact must be in syzygy. So this is the first time in history that the word syzygy is used in connection with a mathematical notion. So Sylvester was aware of the importance of studying relations. And the development of the theory was related to the invariant theory, which was very, it was as to quote again Sylvester, it was the capital of modern algebra, but modern in the sense of the 19th century. Actually, Sylvester says in 1864 the following: so as all roads lead to Rome, so I find in my own case at least that all algebraic inquiries sooner or later, and at the capital of modern algebra, over whose shining portal is inscribed the theory of invariance. So people were very much fond of the theory of invariance in the 19th century, and that came also from that followed the introduction of homogeneous coordinates by Plücker in 1830, and since the introduction of these coordinates, people became interested in the study of invariance, meaning of that they attached, for example, invariance of plane curves. They tried to attach numbers that are independent on the change of coordinates. So they soon realized that this invariance is actually invariance under the action of a group, and they arrived at the following problem. So if G is an algebraic group over a field, let's take it algebraically closed, for example, a subgroup of GLN or a finite group or anything alike, which acts algebraically on k to the n, this induces an action on the algebra of polynomials. Then the problem was to find the elements of S which are invariant under the action of G. So of course this set of invariants is a sub ring in S. Well, and here I just can give the most famous example, like if we take G, the full symmetric group, acting by just by permuting the variables, then we get all these symmetric polynomials, and we know that any symmetric polynomial can be written as a polynomial in the fundamental symmetric polynomials. So actually this is again a ring of polynomials, but this doesn't happen all the time. So we have rings of invariants which are not necessarily polynomial rings. And the first question related to this problem is, and that question was asked by Hilbert, was to decide whether SG is finitely generated. And well, this is the 14th problem on the famous list of challenges of Hilbert. And well, Nagata proved that the answer is no in general, but however Hilbert himself proved that the answer is yes if the group G is reductive. Okay. And second question. So suppose that this was finitely, SG was finitely generated, we would like to know how many polynomials, independent polynomials, invariant under the action of G are in each degree. In other words, compute these dimensions. And again, Hilbert found the astonishing thing that this function behaves like a polynomial for large enough D. Okay, so that was somehow the historical development of the historical beginning of the theory. Let's become now more precise and talk about Hilbert function and Hilbert polynomial. Well, of course, you all know these things, but I would like to put this in the context of the syzygy theory. So what is the general setup? So S is the polynomial ring. We consider M to be a graded, finitely generated S module, and we consider a Hilbert function HD of M, which is the dimension of the piece in degree D of M. Okay, and the famous, the classical theorem is that the Hilbert, this is the Hilbert function. The Hilbert function is polynomial for D large enough. So what was Hilbert's idea? So first of all, he analyzed the case of if M was free. So if M, so the first cases, simple cases are the following. So if M was free, for example, if M was S, then it's pretty clear that so HM of D, this is N plus D choose N, and this is polynomial, so we can write it as N plus D times D plus 1 over N factorial, and this is a polynomial for any D bigger than or equal to 0. And this is 0 if D is lower than 0. So this is okay. Again, if M is a free S module of rank 1, so it's a shift of S by a degree D, or maybe let's put A because D is standard for the degree here in the Hilbert function. So then HM in this case is HM of D is HM HS of D minus A. So again, this is polynomial for D at least A. Again, if M is a direct sum, S of minus A I, then HM will be a sum of h s minus ai. So this is polynomial for d, at least the maximum of all ai's. So for free sorry, for free modules it's all fine. So that's obvious. But what to do next for any module? So that was one of Hilbert's brilliant ideas. Namely, he proposed to approximate an arbitrary module by a free module. And this approximation, the meaning of this approximation is the following. So if m is arbitrary, then we try to approximate. So in which sense? M was finitely generated, so it had a finite number of generators, meaning that we had an epimorphism from, and let me keep the same notation. Okay. So S of minus j to some powers beta 0 j over j. So this is a free module. To, I'll just write this. I'll denote it by f naught. To m goes to 0. And in order to have the best approximation possible, we would like to so we have this. We would like to have this epimorphism, which corresponds to a minimal generating set, meaning that we remove as much as possible from the generators those which depend on other generators. Okay, so now we can consider the kernel of this map, and the hope is that if the kernel is again finitely generated, we can do the same thing, replacing m by k naught. So the first question Hilbert asked himself was whether this k naught was again finitely generated. And this is what we know today as the Hilbert basis theorem, that k naught is globally generated. And the proof was really was so much different from what was done till then, that made Gordon, who was considered to be the king of invariants, say that this was not mathematics, this was theology. But later on he decided that, well, theology is still good for something, so you can prove things using theology. Hilbert actually proved that something was an existence theorem of a finite set of generators without finding those generators. That was the novelty in the approach. Okay, so this is globally generated. We can do the same thing and consider a finite number and a minimal set of generators, and we can get a new free module with an epimorphism to to k naught, and we can iterate this procedure. So in this way we get a free resolution of M as an S module, and it's also a free graded resolution. And now if this resolution was finite, then it will be over, because Hm of the Hilbert function of M would be just the alternating sum of all the others, and we have seen that for free modules these functions are polynomial. So the second question Hilbert asked was, is this resolution finite? And again, that's the second remarkable fact. That's what we know today as the Hilbert syzygy theorem, that after at most n plus 1, n steps, the kernel becomes free. So we can stop the procedure. So the moral is that to any module finitely generated and graded, we can associate a finite free resolution over and graded over S. And now the proof of this theorem is over now. So Hm is sum minus 1 to the I Hfi, which concludes the proof. And we see that from this is the inception of the theory of minimal resolutions and the theory of syzygies, because now we can go back to the words of Sylvester. So we can, for example, if we look at the elements in the kernel of this map, well, elements in the kernel are just relations. So that was the initial meaning of Sylvester's talk. Let's go now to the talk about minimal resolutions in general and Betti tables. So as before, M is a finitely generated graded S module, and a minimal resolution is a free graded resolution over S, such that the image of every differential in this this complex will land in the will have coefficients in the irrelevant ideal. So such that if we denote by M underlined the irrelevant ideal, so the ideal generated by variables in S, and phi plus 1 of fi plus 1 is in M times fi. And from Nakayama's lemma, which holds for graded modules, we see that it's the same as this definition. So it amounts to choosing at each step a minimal set of generators from the kernel. So it's the same as Hilbert's. What does it mean to be minimal? So the meaning of this fact is that if we reduce this map modulo M, so if we pass to the residual field S over M, then all the differentials will vanish. So they all become 0 mod M. So or we can see these FIs are free modules. Hence, any Fi plus 1 is represented by a matrix where the entries are polynomials. And this condition is equivalent to saying that there are no constant non-zero polynomials in these matrices. It's the same thing. Okay. And the fundamental theorem of minimal resolutions is, I don't know who was the first who proved that, but you can find a full proof in Eisenbad's book on commutative algebra. You know, the big one. There is another one, which is also a great book. It's called The Geometry of Syzygies. I highly recommend it. So minimal resolutions exist and are unique up to isomorphisms. Isomorphisms of complexes. So these maps are not unique because we can apply automorphisms of each factor, modifying the matrices, but the terms are unique up to isomorphism. Okay, so we get for any M, get a minimal resolution. And we will speak about the minimal resolution of M, which is unique up to isomorphism. Now, what are the Betti numbers? The graded Betti numbers. So for the minimal resolution Fi plus 1, Fi, F1, F naught to M to 0, the minimal resolution, every Fi is a direct sum, can be written as a direct sum S minus j to some beta ij. So we collect together all the common terms. So if there is one term appearing many times, we collect them together. And we consider this power here. So this is actually how many times S minus j appears in the decomposition of Fi. And this beta ij's, so we get a bunch of positive numbers. So beta ij are called the graded Betti numbers. of M. Okay. And in order to keep track of these numbers, we usually put them in we organize them in a table which is called the Betty table. And this can be a bit tricky. I will explain in a second. So we don't organize them as you might imagine, just a matrix beta ij, but we organize them in the following way. So here we have 0, 1, s. Here we have I plus 1, j. On the first column, we organize the beta 0i, beta 0i plus 1, beta 0j, and so on as expected. But in the next column, we will put beta 1 I plus 1, beta 1 I plus 2. So there is a shift by 1 in the first column. Beta 1 j plus 1, and so on. In the s column, we will put beta s I plus s. Here we have beta s I plus s plus 1 up to beta s j plus s. So what's the reason of doing that? Well, in the first column we read the generators of the module. So there is no mystery about the first column. We have exactly beta 0i generate. So suppose we take a minimal set of generators of the module M. So we have beta 0i generators in degree I, beta 0i plus 1 in degree I plus 1, and so on. So that's fine. But what are the meanings of these numbers? So here we have relations between the generators. This is the meaning of a syzygy. Here we read the number of linear relations, beta 1 I plus 1. So on the rows actually we get, so if we imagine that we had arrows on the rows, then we would get the linear relations. On the diagonals like that, we would get quadratic relations. If we descend one more, we would get cubic relations, and so on. That explains why we organize the Betty table in this way. And there is another reason, which I will explain a bit later when I will talk about causal cohomology, because that would be a real table of dimensions of the causal cohomology spaces. And now let's see some sorry, before going to examples, let me explain how to recover the Hilbert function from these Betty numbers. So the Hilbert function is just, we have to look at the what happens in degree D, and we write down all the dimensions in degree D. So if we do that with this notation, which we have to keep in mind, we obtain that the dimension of MD will be precisely the alternating sum of minus 1 to the I beta ij n plus d minus j, choose n, and the sum is over I and j. So this is the precise formula relating or recovering the Hilbert function from these graded Betti numbers. And we see from which range, in which range it starts to become polynomial. We need all these numbers to be positive. So the moral is that beta ij completely determine hm. The converse is not true, and we'll see in a moment one example when we have different Betti numbers but the same Hilbert function. However, there is a weaker converse which is true, meaning that if we denote by capital Bj the sum over I minus 1 to the I beta ij, so we take for any j in this Betti table we look on the anti-diagonals, so, and we take the alternating sum. We get a number which we call capital Bj, and then we can recover this Bj from the Hilbert function, which is in this formula we apply for d equals j, and if we do that we see that the coefficient here of Bj is 1, so we get that Bj is hm of j minus the sum of the others, bk n plus j minus k, choose n. So we can reconstruct inductively these alternating sums, because here we only have bk's for k lower than j. So we do it step by step if we know the Hilbert function. But this is only the alternating sum of the numbers on the diagonal. So it's not at all true that the numbers themselves are determined. And let's see one example. And the first example is with points in a plane, and precisely 4 points in a plane. With 3 points in a plane, we can recover the Betti numbers from the Hilbert function. But with 4 points in a plane, this is not true anymore. So let's give an example. For distinct points, to make things simple, in P2. So if we take 4 points in P2, we have 3 possibilities. So the first case is that no 3 of them are collinear. The second case is that 3 are collinear and 1 is outside the line determined by these three. And the third case is that when all four are collinear. And let's analyze one by one these cases, see what we get. I should probably keep this here, so let me rewrite the in some books, like for example Eisenbach books, you will find the Bethe table reverted because they use Macaulay, and this is the Macaulay notation. I don't use Macaulay, so I'm not familiar with this program, so then I just copy what's in this complex. So Fi beta ij. Okay, so in the first case, we can suppose that these points are coordinate points. So these are 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the fourth point is 1, 1, 1. So this is P1, P2, P3, and P4. So these are the 4 points. Now let's find the generators of the ideal. So the ideal is generated by two quadrics. And these two quadrics can be taken as this is the drawing is not very good. So if we drew this, you can imagine. Well, geometry is anyway is the science that allows doing correct reasonings on the incorrect drawings. So if these were the 4 points, then we could take two quadrics passing through these 4 points, then they will intersect precisely along these 4 points. If you wish, in this correct picture, we could take two degenerate quadrics like this one and another one which is 1, 2, 3, they have to pass through these 4 points. Well, I don't know. I will stick to this. Yeah, this is a better picture. So in our case, we should take one quadric to be this one, and another one to rule the lines. Like, for example, we can take this one to be the second quadric. Okay, and they intersect in precisely these 4 points. Anyway, so we get the ideal is generated by two quadrics. So Q1 and Q2. And these quadrics will only have one relation, which is the following. So Q1 times Q2 is Q2 times Q1. Well, this might seem a little bit silly. This is a trivial expression, but it's not trivial from the point of view of syzygies, because this would give one relation. And this will be exactly a quadratic relation because of the coefficients here. So the degree of the relations are read in the degree of the coefficients. So the minimal resolution looks like we have the ideal of this. Let's denote by x these 4 points, p1, p2, p3, p4. So we get the ideal of x. This is generated by 2 quadrics, and we have one quadratic relation. So the difference here stands for the degree of the relations. So if we look at the homogeneous coordinate ring of X, then we will obtain this minimal resolution. So the bottom line is that the Betti table of X, when I say the Betti table of X, I mean the Betti table of the homogeneous coordinate ring of X, is the following. So here we have 1 in the upper right corner. Then we have 2. So we have no linear relations. So we draw one line. We have 2 quadratic generators. And there are no linear relations between these generators, but there is one quadratic relation. So here we would have 0, 0, 1, 2, 1, 2, and so on. And all the others are 0. So this is the Betti table of X. So if we apply the formula, we get the Hilbert function. Hx will be the following. So Hx is of 0 is 1, of course. Hx of 1 is 3, because they are not all on a line. And Hx of 2 is 4, meaning that they impose independent conditions on quadrics, and so on. So it becomes stationary at 4, which makes sense because we have 4 points. So this is the Hilbert function. Now for the second case, what was the situation? So we had 3 points on a line and 1 outside the line. And in order to generate the ideal, we would need 2 quadrics, but 2 quadrics will not be enough, because once we have a quadric in a line, which in a plane which passes through 3 points on a line, that quadric or conic must contain the line. So if we just look at quadrics or conics, if you wish, we cannot get rid of this line. So we can choose 2 quadrics. So the ideal generators of the ideal. We have 2 quadrics, conics. I say quadrics because it's a kind of automatic. In general, we have quadrics. But we need 1 more cubic in order to rule out this, to get rid of this line. So if we take 2 quadrics, for example, this quadric and this quadric, we get this line and this point. And to get rid of this line, we need one cubic. Passing through these points. So this is the cubic. Okay. And now, what are the Betti numbers? So we will have the ideal. So the ideal is generated by these guys. So the ideal will be generated by S minus 2 copies, plus S minus 3. So this is for the two quadrics, and this is for the cubic. And if we analyze, because we can write this in coordinates, if we analyze the relations, we will notice that there is one linear relation and two quadratic. One linear relation and one quadratic relation. S of minus 4. And we can actually write down the matrices, so I will just do it. So if we have this line is A, this line is B2, sorry for the notation, this is B1, then we have the quadrics are AB1, AB2 are the quadrics, and the cubic is of type F1 B1 plus F2 B2, and this matrix is given by AB1, AB2 and C, and this matrix here is B2, F1, minus B3, F2, 0, and A. So I erased the other resolution which was here, but it's quite clear that this is different. So the Betti table, in this case, becomes, so we have again a 1, which would correspond to an S, which is here, which I will not write anymore. Then we will have 2 here, which would correspond to the 2 generating quadrics, a 1 here, which would correspond to the cubic. And now let's write the relations. So we have 1 here and 1 here. So the Betti table, remember that in the other case we had 0 and 0, which is consistent with the formula over there, because the alternating sum is the same. Because now the surprise is that the Hilbert function of this configuration of points is the same as the Hilbert function here. So hx of 0 is 1, hx of 1 is 3, because they are not on a line, but they impose independent conditions on quadrics, and so on. So we see here that we have 2 different configuration of points. They are essentially different, but the Hilbert function cannot detect which is which. So Hilbert function can detect many things, but not as many as we wanted. So that already shows that Betty numbers, graded Betty numbers, are better than Hilbert function. Well, however, in the last case is completely different. So even the Hilbert function is different. So if they are on all, so this is the third case, and the last case, if they are all on the line, then we need, in order to generate the ideal, by this line, and we need a quartic. For example, well, we can take a degenerate quartic or something like that. And then, if we write down the Betty table, will be 1, 1, no quadrics, no cubics, but one quartic, and we will have one obvious relation, which is exactly as in the same case given by the trivial relation between the two. And we can compute the Hilbert function out of this, and we see that the Hilbert function is completely different. So in this case, Hilbert function can say whether the points are on a line or not, but it cannot say whether 3 are on the line or not. So if we want to go deeper in the analysis of the geometry of an embedded variety in a projective space, studying these Betty numbers is the right thing to do. And I think I will stop here for today. The next week, my intention is to speak about, to give more examples, to discuss the Hilbert-Birch theorem, which gives a general pattern of resolving ideals of points in a line, Koszul cohomology, and then pass to the relations between Koszul cohomology and the geometry of varieties. Okay, thank you very much.